Welcome back to another episode of Detection Dispatch, the podcast that became a podcast just this last year, covering all things detection engineering. And what a time it has been for our world here. This detection engineering movement just hit a pretty big milestone. This is our first episode back since dropping the inaugural first of its kind detection engineering report that just literally dropped this past week. And we're super excited to share it. We had a SANS webcast about it earlier this week. Today, we have someone who not only contributed to it, helped shape a lot of it, but also someone who's just continuously pushing this space, the detection engineering space forward. Very special, very beloved, and returning guest of Dispatch. And for those of you that are not following Andrew VanVleet, if you're not already, you absolutely need to be. Well, Andrew, welcome back to the pod.
Thanks, Alex. Appreciate it.
It looks like we got a wonderful crowd here. As I mentioned, we have this incredible milestone, this initiative that we've invested in to give back to the community, which is really the heart of what Dispatch is all about. We partnered with SANS to capture the state of detection engineering, which is this window of time into this movement. We share what engineers are spending most of their time doing, what they like doing, what they hate doing, right? What they get paid, right? Collectively, they think are areas that need improvement, areas that suck, areas that need work, right? It revealed a lot of big insights, right? Specifically for this particular episode, we saw that 42% of detection engineers are preferring to build custom built detections, right? They want to take ownership and accountability in deciding what detections they want to build, right, and implement in their org and, around their unique setups. And out of, these detections, behavioral based kind of ranked and emerged as the best of the best in terms of the ones they're building. That's what brings us to today's episode, right? We want to dive into exactly, kind of like this, right? The custom built strategies around this Kerberoasting, behavioral correlation. This episode will be a little bit of a different take because it's more of a live workshop, right, versus an interview format that you may be used to. You're getting a front row seat because we are in a virtual setting. This is going to be a fantastic way to, Andrew, right, where we're going to break down the attack, explore multiple ways that the threat model has in terms of variations. So if you want to bring your AI note takers or your snippet tools, your screenshotting, or if you want to, if you're still writing notes with pen and paper, are we still doing that? Writing notes with pen and paper? I don't anymore officially. I just threw out all my notebooks. But Andrew, why don't you kick us off? For those of you that don't know you, tell us a little bit about you, what you do, and what you've got over in building out this super intriguing resource and research about the T1558.003 technique.
Yeah, appreciate that, Alex. So about me, I'm a detection engineer. I've been in the industry for about 20 years now. I started off in the intelligence community doing intelligence analysis, particularly of cyber threats, really very much like an analytic thinker at heart. And I've just been doing, threat detection, threat hunting for at least the last decade. Is definitely my passion. It's what I love to do. It's a puzzle to solve. It's very much what I enjoy. So the stuff we're going to do today, when we were here on the Detection Dispatch, we kind of went over some of the strategy. The whole background on this is as I came over to a new position, we took the opportunity to step back and think about how we do our detection engineering. Kind of the process we go through, the strategy that would make us most successful. And a lot of the blog series that I wrote is really based on a lot of that research, a lot of thinking, that strategic stepping back and taking a look at things. Today, we're going to go more specific into what I call technique analysis or detection modeling, where we're going to be using an analytic tool to take apart an attack technique, really dive deep into it, understand what it's doing, understand its procedures, and then to build a detection strategy for how we can comprehensively cover the detection. So I'll share my screen and launch into this. Let's get started with a review of basics. As detection engineers, our goal is to create detections that cover an attack technique as comprehensively as possible. That means we need to identify as many of the possible attack procedures as we can. Otherwise, the attacker's still gonna have an opportunity to slip past our defenses, right? So taking my terrible adaptation of a football play up here, we want to not have that maroon guy out there on the left that we're not aware of, we're not paying attention to, we have nothing in place for him, and he just moves on right past us, right? I am going to be using a very specific definition of procedure today. This is not the same definition that you're going to see used in the attack framework. When I say procedure, what I mean is a distinct set of steps or operations that will implement an attack technique. If we take that as an attack technique, the path from A through to E through B is one distinct procedure, one distinct set of operations. And a second procedure would be the path via C, right? So there's two procedures identified in that particular model. So that's going to be how I'm going to be using that term going forward today. If you have never seen these before, we're going to be using what I call a detection data model. This is an analytic tool that will help us identify unique procedures and develop a strategy for detecting all or as many of them as possible. This is just giving you an introduction to it. You don't need to digest this particular model. We're going to go step by step together building one today. So this one is a model for T1207 rogue domain controller. Just gives you an idea of what it's going to look like. The idea is that it maps out the essential operations, the specific procedures, the specific things that have to be completed in order to implement an attack technique. And then it also maps in the telemetry available for us to be able to observe those particular techniques. So yeah, we're going to be building a DDM for Kerberoasting today. This is E1558.003 according to MITRE's framework. Steps we're going to go through. So again, this is kind of our overview. This is just your roadmap. This is kind of our 10-step process for analyzing a technique. We're going to walk through 1 through 9 today together, and then we'll be coming back to these steps as we go. So let's just dive on in. Step number 1. Step number 1 is to start with what you know. So taking Kerberoasting, we are going to just take the quote pretty much from MITRE for this. Adversaries possessing a valid Kerberoasting TGT may request one or more ticket granting service tickets or service tickets for any service principal name. We're just going to call them SPNs. Portions of these tickets are encrypted with the SPN's password hash, which makes them vulnerable to an offline brute force attack that may expose plain text credentials. If you're not familiar with this attack, basically the idea here is that these service tickets that you request to be able to gain access to a service have a known structure so that if you guess the right hash and you get the expected output, it means that you used the right input. So you can take the service ticket, you can take it offline, you can start throwing hashes at it in a typical brute force. Once you get the expected structure out of your decryption, then you have identified the correct password that went into doing that. So that gives essentially 3 operations to start with. We have enumerating SPNs, we have requesting a service ticket, so you have that ticket to crack, and then we have cracking that hash. You notice that I put host any on each of these because any host in the network can request an SPN. Any host, can enumerate SPN, any host can request a service ticket, and any host, even offline, can be used to crack that hash. This gives us our initial brush in our detection model as to what we know so far. So the first thing we're going to do is choose an operation, and we're going to go deeper. So we're going to expand our knowledge on what we've got so far, which is very rudimentary to begin with. The first thing we're going to choose is this operation of enumerating SPNs, right? So we just start by thinking about it. What do we know of ways to enumerate SPNs in the directory? What tools are available? I did a quick Google search, Kerberoasting, pulled up all the tools that came up. We have Rubius, SetSPN, various public tools. So first thing we're going to do is take those tools and look at them, see what they do, throw them in a lab, run them, capture them, put them in IDA or Ghidra, look at the calls they make, read the source code, just start digging into them to get an idea as to what these tools are doing in order to enumerate SPNs. When we do that, we categorize them, we find out which ones use the same approach, which ones do it different. In this case, we find out that there's using 2 different ways to enumerate SPNs. One is using LDAP, and one is using ADWS. You can also see that there's clearly a favorite, right? Almost every one of the public tools is using LDAP to enumerate SPNs, all of them. So yeah, here's our category. You can see that every tool is basically using LDAP from a quick Google search. So we categorize them. This gives us 2 possible techniques or procedures for enumerating SPNs in a directory, right? Are there any other ways that we can think of doing it? We've got LDAP, we've got ADWS. What other means do we have to query the directory that could possibly be used to enumerate? So maybe there's the security account manager RPC interface. This is what net.exe uses. So when net use whatever, it's using the SAM RPC interface. So maybe that one worked. Clearly, we can get domain user information from there. And how about WMI? WMI is a beast on Windows. It can query just about everything. So let's take a look and see what WMI can do. So I'm going to kind of jump forward. We normally go into this research to save us a little time. I'm going to give you a spoiler. Both of those do allow us to enumerate directory users, but neither of them appears to support querying or retrieving the service principal name attribute, which is a critical element for Kerberoasting because we have to have that service principal name. So neither of them is going to support that. We can throw those out. So those are two options that are not on the table for an attacker. This is good. The next step is we're going to add these to our DDM, right? So we're going to come back to our model. We're going to expand out from what we knew previously. With a DDM, typically we're going to go laterally when we're talking about consecutive steps, and we're going to go vertically when we're talking about things that implement higher steps or different levels of abstractions. I've added some arrows going down from enumerate SPNs to show that we have two different ways of implementing that. One is sending an ADWS request, and one is sending an LDAP search request. So we've got those two procedures. You can see that our graph is now split into the two procedures that we've identified for this. So this is good. Let's move forward. Next step is to do it iteratively. So we're going to expand our knowledge on another operation. This time we're going to take the LDAP operation. We're going to start digging into that one specifically. So let's look at it. What is the LDAP search that's being used to enumerate these SPNs? So the easiest way is to first just survey the tools, figure out what other people who've solved this problem did to solve it. So I put them into a table here. If we look at Rubius, they're doing this service principal name equals star in their LDAP query. SetSPN, same thing. They've got this weird star/star notation, but same idea. Packet using the same thing. Invoke Kerberoast with PowerShell Empire is the same thing. The only one that was different here that really stood out is that Impacket has this stealth mode that you can configure via the command line arguments. That one was interesting because it doesn't specify that it's looking for accounts with a service principal name. That's interesting. So digging in a little bit to that, we look at the code for what their stealth mode is, and we find that instead of filtering for service principals in the search filter or on the query side, the server side, they actually add the service principal name attribute to what they're asking to be returned, and they ask for all of the users. So literally give me every user in the domain, include the service principal name attribute, and then on the client side, they loop through all these users and throw out the ones that don't have an SPN. They end up with the same results, but the signature of that LDAP search query is going to look really different. That gives us two options an attacker can filter on the server or on the client. The important part here is that if we're trying to build a detection and we choose to use this service principal name equals star, we're going to miss stealth mode or anything else that chooses to use that filter on the client side approach to this attack. So that's a good thing for us to have noted. One thing to note is that this is being done via an LDAP search, but there's no reason we can't do this via that ADWS option as well. Here's an example PowerShell script, thanks to Adam on the call, who's the one who wrote this. So this one will actually use Active Directory PowerShell, which uses ADWS, to go out, request all users, including the service principal name. Then it will loop through those service principal names and result or throw out the users that don't have one, resulting in a collection of only users with SPNs. So we get the ADWS filter on client approach. I can tell you right now that I'm guessing your EDR is going to miss this because they're just not looking for this filter on client ADWS approach. Try it out. Let me know what happened. Next step, we're going to add what we learned back to our DDM. Again, our iterative process. In this case, we have these two options. They apply to both our ADWS and our LDAP procedures. On our enumerate SPNs operation, I've added a note that says we have two options, filtering server side, filtering client side. So now we're going to go again, iteratively through this process. So I'm actually going to fast forward right now for the interest of time. The process that we would go through would be that we would go at each operation. So we dig into ADWS, see what we can find. We dig into requesting a service ticket, see what we can find. We're going to research it, add what we know back into our DDM. I'm going to fast forward now and tell you what we've added after we've gone through this full process. Here's what we've added to DDM at the end of our process. We've learned that an attacker requests one or hundreds of service tickets. So I've added a loop here to show that this is an iterative process between request service ticket and send service ticket, so that it's clear that this is going to happen potentially one or many times. We found out that they need a valid TGT in order to request a service ticket. So I've noted on requesting service ticket that you need a valid TGT. I've also discovered that you can downgrade the encryption to RC4, making it easier to crack, but you don't have to. And also, you might not have like RC4 might actually be your default in your environment. If it is, you don't have to request to downgrade it. So I've added an optional thing that says downgrade encryption to note that an attacker may request downgrade RC4, but they, then again, may not. So once we have our DDM here, we are done with this portion, right? The point where you realize that you're done is where you can look at each operation, you've investigated them, you've researched them, there's no question marks anymore. You understand how it works, you know what it looks like on the network or what APIs it's calling, you fully understand what's happening. That's the point where you can tell that you are done. A DDM is an analytic tool. It's not itself a scientific process. Multiple people can go through this process, and the value is in making you think through what you know, putting it down on paper, iteratively expanding that knowledge. Two DDMs by two different people may look a little different, and that's okay, right? As long as we're getting the operations in there, we're going through that process for identifying the procedures, that is absolutely fine. So our next step is that we're going to add in the available telemetry. As you've been going through this process, you've probably started to encounter some telemetry to help you see these things. But now is the point where we make a concerted effort to see what telemetry we can find and have available. We're going to be looking at operating system logs, our EDR, maybe Sysmon, or any other source you can think of, event tracing for Windows, anything that might provide you some visibility in these operations. And then we're going to add these back into our DDM. Here you can see that on receiving an LDAP search request, if you have CrowdStrike or Defender ATP, there's actually an event there that logs what the LDAP request was. So that's excellent. There is Windows event 4768, a Kerberos service ticket was requested. That happens when the domain controller sends the service ticket. CrowdStrike has parallel event there as well, so I've added those in. Notably missing is that I could not find a Windows event for logging an LDAP search request query. You got to have that EDR, CrowdStrike, Windows Defender, whatever your EDR might be. There's no out-of-the-box Windows log for that. And there is zero available telemetry for EWS requests. There is a weird putting it in a debug state, which is extremely verbose, and you could probably never convince your domain controller team to do it on your prod domain controller. There is no kind of prod viable, scalable method that I am aware of to get any insight in that AWS. So this gives us our DDM. We've got our telemetry, we've got our DDM in place. Now, the next step is that we're going to identify other possible paths. This is important. This is where we find that maroon guy in the left field. We start thinking through our model and we start asking ourselves, are there ways to get to later operations without having to perform the earlier ones? Or are there different paths? In this case, the model is visual. It makes it easy to think through this process. We look at our model. Our first step is to enumerate SPNs, right? We have two options. We kind of already talked about other options like SAMR and WMI, and we couldn't find any. So we seem like we found most of our options there. What if we skipped that step? Could we skip enumerating SPNs and go straight to requesting a service ticket? It turns out we can't, because to request a service ticket, you have to have the name of an SPN. So chicken and the egg problem, I've got to find out what the SPNs are. The only way I can do that is enumerating the directory. So that's not really an option for me. So then let's look at the next one. If we can't skip enumeration, what if we could skip requesting the service ticket? Let's just find some other way to gather service tickets and then take those offline and crack those. So are there ways to do that? It turns out, yes. If we have a man in the middle position on the network, we could intercept these TGS request messages on the wire and extract out the service tickets there and take them offline and crack them. We don't ever have to enumerate or request a service ticket. The other option is if we have access to one or let's say many endpoints, these service tickets are cached on the endpoint. So we can just take them off of the endpoint, take them offline and crack them. We don't really need any special action. We don't have to request it ourselves. Obviously, we will only be able to get what we can see and someone else has requested. We're narrowing down the number of services that we might be able to crack. On the other hand, we're not going to be seen requesting service tickets. We're going to add those options into our DDM here. I've added two more operations here showing intercepting tickets and harvesting tickets that just jump straight to cracking the hash. At this point, there's not really any more operations to explore. I can't think of any other procedures that would work for this. So we're kind of done, right? We've got our DDM, we've got our telemetry. We've finished researching, analyzing, and modeling this technique. So it's time to get forward and start using it. The first thing we're going to do is list our distinct procedures. Easy to do, but useful just to make sure that you have gone through that process of getting it out of your head, putting it on paper, and making sure that you've not missed anything. So we've got 4 procedures that we've identified, 4 distinct paths through this model. There's enumerating SPNs via LDAP, enumerating them via ADWS, sniffing the TIFIX off the network, and harvesting them off of endpoints. So these are the procedures that we ideally want to be able to detect. And as we're putting together a detection strategy, this is what we're going to be trying to tackle. Step 8, we're going to skip. That's documentation. We're skipping it, not because it's unimportant. It's actually really important, but it takes a lot of time. I'm actually going to put out a blog post later that talks about how we document this and why we do that. But for now, we're going to skip it. We're going to jump to step 9. Step 9 is using the model to create our strategy. So remember, our goal is to cover all of these techniques as comprehensively as we can. You're going to find that we are going to get skunked on some of them, but we have some opportunity on others. But we want to create our strategy at this level so that we make sure that we are making a comprehensive detection for this technique and not just putting up something here and something there and leaving all sorts of gaps that an attacker can go through. So here's the process we're going to go through. We're going to look at our model, choosing operations, and figuring out which ones give us opportunities to detect. The first thing we're going to do is address the elephant in the room. Intercepting tickets off the network and harvesting them from endpoints are valid procedures. If an attacker has the position on the network or enough endpoints, they can do this. There's probably nothing we can do to directly detect this. This is just going to be a gap. And that's okay. We want to document that we know this is possible, but this is going to be a blind spot. We'll come back to our blind spots later. Moving past our blind spots, our first really good option for detecting this is going to be right here at this service ticket request. The reason for that is this is kind of a bottleneck in our model. It's a spot where all of the procedures that we're going to be able to detect are going to combine together. And we have telemetry, right? We have that service ticket request log. So ideally, if we can use that log to identify the malicious activity, then we could have nearly 100% coverage of these 2 procedures right here at this spot with 1 detection. And that's really where we want to be in our best scenario. Unfortunately, in this case, requesting a service ticket is a fundamental part of Kerberos, and it happens all the time. So that makes it very difficult because we can identify 100% of these activities, but classifying them as whether they're malicious or benign, that's going to be really challenging. We have to find some way that the attacker is going to stand out from the normal traffic. So there are a couple of options we have here. One is we could make a detection for when they request to downgrade the encryption type. We talked about how they don't have to, but if they did, that might be potentially malicious or suspicious, especially given our environment. If that's uncommon, that could be a very suspicious act. So that's an option. The other option we have is that we could look for a lot of requests from a single source. You know, if they're going to be requesting, say, 100 tickets, so they increase their chances of being able to crack one successfully, that might stand out above the normal frequency of what people request tickets for. Depending on the noise in our environment and what's normal, we can probably establish a threshold that's below this is normal and above this becomes suspicious. Anybody requesting these tickets above this threshold, they're probably suspicious. Now, we have to remember, though, that an attacker could just request 1 ticket or 2 or 3. They don't have to request a ton. And there's nothing that says they have to request them all today. They could request them over the course of our lifetime. Really, there's no real restriction there. So it is possible that they could request those at a frequency that will stay below our threshold, and we still won't be able to catch them with that. So it's not our silver bullet, but it's an option. The other option we have here is that we could create a canary. So we could make a service account that has an SPN that has no actual purpose and should never have a service ticket requested for it. If somebody does request a service ticket for it, that's probably malicious. So that's a good option. Now, we aren't gambling on whether or not the attacker roasts our canary, but it is an option. So those are the options we have here at this particular spot in our model. None of them is our 100% coverage, silver bullet, perfect solution. Some techniques have that, some don't. I picked this one because it was pretty illustrative of what we typically go through when we're doing detection engineering. Let's look at a different spot in our model and see what options it provides us there. At this point in the model, we're dealing with our enumeration. So we're going to be looking for when the attacker is enumerating those SPNs. Unfortunately, at this point in our model, we have two procedures that we have to deal with. So ideally, we'll be able to create one detection for both, or a pair of detections that together will cover all of this, but we'll just have to see what our options are. At this particular point, if we have that telemetry on LDAP search requests, a very good option is to look for a query that is either looking for service principal names client side or requesting service principal names attributes so they can build it on the client side. That could be a very good option for us. It could give us potentially very good coverage, but only of the LDAP procedure of this attack technique. Ideally, we would be able to do the same for ADWS. And if we could have telemetry for it, between the two of those, we could actually have very good coverage of enumerating SPNs for Kerberoasting in our environment. Unfortunately, I'm not aware of any telemetry for ADWS. We have the option of looking for the LDAP search, but we are unfortunately blind to enumeration via ADWS. At this point, we've gone through all of our options here. Obviously cracking the hash, that's going to happen offline. We don't really have any options for that. When we're putting together a detection strategy, we don't have a silver bullet. We didn't have a great option that was just the one spot to cover it all, easily identify that it was malicious. That just didn't work out this time. Our best strategy at this point is to make the best possible coverage and document our known gaps. If we took all of the options we've identified, all 5 of those particular detections, we put them into production, we'd have a pretty good coverage mix. So in order to not be detected, an attacker would have to enumerate with ADWS. And remember that most of the public tools are using LDAP. So if they're taking it off the shelf, that's not going to be what they're going to be doing. They'd have to implement their own. They would have to not downgrade the encryption. They would have to request the tickets at a slow enough rate to stay below our threshold and not roast our canary. It is possible for them to do that, but the odds are probably leaning in our favor at this point. That's a lot of things for them to be able to successfully do, not being aware of what we have in place. So at this point, we've probably tipped the scales so that the probability favors us if they're using this attack technique. So then we've got our strategy. The next thing we need to do is finish documenting our research, especially our gaps. This is the point where we engage the rest of the organizations, the security teams, the strength and policies that are in place. As we do our research here, we find out that because it's a brute force attack, if we were using strong encryption and strong passwords, this attack wouldn't be very viable to begin with. Whether or not we could detect it, it wouldn't work well. So this is the point where we reach out to those teams and we have really good research, really good documentation, and we can come to them with a strong position to say, hey guys, we need to make this change, and here's why. So we harden up the environment. Next thing we do is we implement our detections. So we take those detections we built in our strategy, we actually put them into logic and deploy them in our environment. At this point, we know which logs we want. We know what the query logic is that we're looking for. So this isn't going to take us very long. So we get these done, we put them out, and we're done. We're finished. And at this point, I'd say good luck to any attackers attempting to Kerberoast us. We're ready for you on this one. Go ahead and roll the dice and see if you can get past us. So there you have it. That's kind of from soup to nuts, the 10-step process for analyzing a technique with a DDM.
That was fantastic. Andrew, what was the driving factor behind implementing this multitude of detections? You mentioned before that it was overlooked by the EDR. There's tons of gaps throughout there. You didn't even have telemetry sources. Where did this inspo come from?
You mean the information, like the research that I did on it, or?
The driving factor behind why you went about implementing this detection.
Yes. Yeah, so the driving factor, I mean, in all of the cases, and this kind of gets into some of the background documents I've written, but the goal that we have as a detection engineer really is to create this mesh that covers each technique as comprehensively as possible so that when an attacker is into our network and they're starting to take the steps to try to get to their goal, right? Mm-hmm. They essentially have to choose an attack technique and a specific procedure. And we want to make it very hard for them to successfully choose procedure by procedure things that we don't have alerts on. So the goal for this approach and this analysis process is to take this technique and make it as ironclad as we possibly can. And there are techniques where you can get like perfect 100%, just don't even touch this, I will know about it. And there are going to be techniques where you're going to just throw your hands in the air and say, the attacker going to have this one, there's nothing I can do about it. But the goal is that if we can push the probability on every single one of them, our coverage up to the maximum possible on each of them, then
Mm.
time after time, the attacker has to be right every single time. And we just push that probability up to the point where they're just not going to be successful, statistically speaking. That's kind of the impetus.
That's fantastic. So it wasn't like you looked at your MITRE technique coverage. There wasn't anything in there for the TI 00, 813, and you just went all in into building out this research. Did it come from a big event?
Now, the way we typically go through, your organization would have to prioritize what you should cover yourself. I suspect that any detection engineer in an organization like 1 or 2 years, or any red team, or anybody in the SOC, if you ask them where are our biggest vulnerabilities, what are the things that make you worried, they could probably already give you a list of attack techniques. They're like, these are the ones that I think we need to cover. Those are where you start, right? So Kerberoasting I picked up because it's in the news like every few weeks, it seems that scattered spider, Chinese threat actors, everybody's Kerberoasting. So that's why I picked this one. You would essentially go through the prioritization, take them, rack them, and stack them, and say, these are the ones that are most critical in my environment. And start there.
Would you say you've had this implemented for some time? Is it ringing any bells? What's your tuning efforts around this? Is it noisy in nature?
Yes, they could. When we're doing a detection, there's kind of two jobs to be done. There's identifying when the event happens and classifying whether that event was malicious or benign. The first job is the identifying because you cannot classify what you cannot identify.
Right.
So, what we're going through right here is really heavy on the identification side of saying, here's how you're going to get visibility into what's going on. On the classifying side is where you start to deal with what's noisy in my environment. I advocate that classification is usually a very environment specific task. What is noisy in your environment may not be in mine. There are some environments that are so small and homogeneous that they can easily say everything but this is bad. Other environments that I have worked in before are very loud and there's lots of different things going on, and it's very difficult to sometimes say this particular thing is malicious. So that
Yeah.
whole process of tuning and getting it down to the point where it's high fidelity enough to actually move into production is very environment specific, like what works in your environment. I will say this though, for any of them, you take your detection strategy, you put them in, you start seeing what kind of noise you have. You start going through that process of filtering, and you're going to come to one of two possibilities. Either you can get it tuned enough that it's high fidelity, and in your environment, you can make a high confidence classification that this is malicious and should be actioned, or you're going to find that it's too noisy. What you do when it's too noisy is you turn it into a signal. Anvologic does this great with the warn modes, right? You put it into warn mode, and then you have something that's going to start aggregating warning signals so that I could say, it's too noisy to say people are requesting too many service tickets, but when I see that they're doing that, and I see that they're doing this and they're doing that, now I can raise a high confidence classification and say this is malicious, investigated. So for any detection you're dealing with, any procedure, you're going to go through that filtering and evaluating it in your environment process. It's going to come into one of those two buckets, or it is going to be one of the frustrating ones where you throw up your hands and you say, I can't do anything about this.
In the detection engineering report, we saw, in line with what you're saying, we're spending most of our time building detections, tuning the detections. As far as how long it's taking us to build the detections, it's not uncommon for it to take over a week. 84% of people say that it takes them over a week to get a detection out the door from the point that it becomes an idea to the point that it becomes ready full detection. How long did this process take you for this technique?
This one probably took me about 2 weeks to research it all the way through. It'd probably be another 2 or 3 days to get the actual detections implemented and put into production. This is not going to be your turn out a bunch of detections fast. I really like to highlight for people that the output of this is not actually detections. Output of this is to increase your attack surface coverage. If I go through this, I find out in this process that my environment's using RC4 tickets and crappy passwords. When I work with the team to argue why we need to move to stronger encryption passwords, I have removed that attack surface coverage without building a single detection. The process we're going through here is really to increase the attack surface coverage, of which detections are one of the possible options we have to fill in those gaps. It is definitely not a fast process. One of the thoughts that I've had that, watch this space is that a lot of this research really is adaptable to all environments. Like once we understand Kerberoasting, anyone could take this DDM that we've created and the documentation we built, and they could implement it in just a week with all the good research. So one of the things we're looking at is how could we share the attack research in the industry better rather than sharing the detections. If you think about a detection, it's a poor vehicle for conveying the research, because when you build a detection, you go through all sorts of processes and decisions that are specific to your environment. Which log source you're going to use? Well, that depends on what you've got. Which query language, how you're going to implement that, what you're going to tune out. All of these are environment specific decisions that may not be the best for my environment, but was for yours. But if I take the research, throw it away, and publish the detection, I've just thrown away all of those decisions I made that might not make this the best detection for your environment, but it made it good for mine. So that's one of the things we're looking at is, what's a way that we could share this research so that every one of us could have this level of research and still have the speed of being able to put out detections and fill those gaps at a faster rate.
I think if you go back to the model, I love the way that you articulated it here and you threat modeled all these different iterations. Just looking at this, people could take back what decisions they need to be doing, what telemetry they need in their specific organizations, and how they would go about implementing their own detection means according
Exactly.
to according to this techniques. I
Exactly.
absolutely loved it. I think there's so much that we can gain. Good luck to the attackers trying to get through to you guys when you have something like this in place. For those listening, if you have any questions for Andrew, now would be a great time to ask those in the chat or to come live. I think this is a fantastic example and very meaty content in terms of what we're used to here, and we're absolutely grateful for that.
I see a question for Josh. What language is this in the LDAP search? Josh, that's actually just the LDAP query filter language. I don't know what that's called, but when you build an LDAP query, they have a specific language that you use to build your LDAP filters. And those are just the raw LDAP filters. So you could plug that into LDAP, you could plug that into AWS. Anything that will query LDAP, you could put those filters in for that.
Yeah. And whereas the AWS, that's in PowerShell, right?
Yeah, I mean, so the weird thing about this is AWS is actually also using LDAP filter queries.
Mm-hmm.
They're just not taking it over the LDAP protocol. So they've built this web interface by which they wrap the LDAP query in like an XML message. They send it over and then they submit it to the directory with an LDAP query, but not using LDAP. So kind of a strange little beast that somehow in its weirdness avoids the logging that captures LDAP searches and yet manages to do the same thing. For those of you who are CrowdStrike users, one of the processes we go through is if we find a situation where we don't have telemetry, that's the point to engage your EDR and tell them, I want telemetry. I've actually got a request into CrowdStrike asking them to please add telemetry for the ADWS. So if you're a CrowdStrike user, their IDEA page, go look at CrowdStrike IDEA I6566 and vote it up.
You made it when your vendor doesn't have the telemetry you need and you're asking for it.
Maybe. I put a request into them a number of years ago for process projection, and they did deliver wonderfully, but it took about a year and a half. It's a slow train.
Looks like we don't have any more questions. Anyone else? All right. Then that about does it. Andrew, thank you so much for this incredible content. If you are not already following him, I think everybody should fix that. You can find a synopsis and overview of this session and how to document a lot of the 4 types of distinct paths and procedures in a blog format that Andrew will be publishing very soon on his threat detection series on Medium. We'll link it here in the chat. And for those tuning in on the replay, we'll link it in the show notes. You can clearly see that he continues to push the space forward in the best way. Andrew, you're welcome back on Dispatch as many times as you please. We need to keep these evolving practices, and we need to keep letting vendors know if they don't have what we need to build solid detection strategies. So for those listening in, join us in a couple of weeks to celebrate International Women's Day, or in our case, month, with a complete 3-week lineup of wonderful ladies who also, like AVV, are pushing the boundaries in the threat hunting and detection engineering space. Until next time, I hope everyone has a wonderful day.
Thanks, Alex. Thanks, everybody, for joining.
Thank you, Andrew.